Now we come to a topic that is frequently confusing, but is designed to help explain why gases behave the way they do. It takes all of our observations, puts them into kind of a compact description, which is known as kinetic molecular theory. And some of these will be familiar, but to just briefly go through kinetic molecular theory, its purpose is to describe why gases behave the way they do. And it has 5 statements or postulates. And those statements are first that gas molecules have random motion, that there's nothing dictating the way gas molecules move. And this could be simply from observation. Gas molecules, there's nothing telling it, oh, move in a straight line in this direction. They simply move in any random direction. The second is that the gas molecules themselves have negligible molecular volume. This is simply what we had stated earlier, that the volume of the molecules is much smaller than the volume that's occupied by the gas. So most of a gas sample is just empty space. And as a result of this negligible molecular volume, then there's negligible forces. There's very little interaction between the gases. Gas molecules do not interact with each other. The next 2 are ones we haven't really seen before, but this is constant average kinetic energy. It means that within a sample of a gas, that the average kinetic energy, providing that the temperature is held constant, is constant. Now, the kinetic energy of individual gas molecules will change, but the average kinetic energy of the whole system does not change at a constant temperature. So at constant temperature, average kinetic energy is constant. And then the last part, still relating kinetic energy here, is that the average kinetic energy is proportional to the temperature. So the kinetic energy, which is the energy of motion of gas molecules, is directly dependent on the temperature of the system. And it's dependent in this equation here, where the kinetic energy is equal to 3/2 times the gas constant times the absolute temperature. Now, where are we going with all of this? Well, the summary statement from these last 2 points is just that at any given temperature, the molecules of all gases, regardless of the identity of the gas, have the same average kinetic energy. So if I have a sample of helium, or a sample of argon, or a sample of chlorine gas, or a sample of sulfur hexafluoride, all of these have different molar masses, different chemical properties, but on the physical property side, if they're all at 25 degrees Celsius, then the average kinetic energy of all of those samples is going to be the same. Let's go through a couple other statements and descriptors from this theory. The first is, what really is the pressure of a gas? Well, pressure is force over area. So what exactly does that mean for a gas sample? Well, it's caused by collisions of gas molecules with the container walls. So that's force exerted by those gas molecules hitting the container wall over the small cross-sectional area that's hit by that gas molecule. That's what actually causes the pressure of a gas in a container. What exactly is the temperature a measure of? Well, again, sort of using that last equation, temperature is actually just a measure of the average kinetic energy of molecules. So we have that equation that relates the temperature to the kinetic energy. We mentioned this one earlier, but we can also remember from early in chapter 5, where we mentioned another equation that relates the kinetic energy, kinetic energy, and that's relates to the speed of the of a material. So we can relate, since kinetic energy is the energy of motion, we can relate the speed or velocity of an object to its kinetic energy using the 1/2 mv squared, where m is the mass and v is the velocity or speed. Now, since both of these equations are equal to kinetic energy, we can set them equal to each other, and this allows us then to relate the temperature of the system to the average speed of gas molecules. And then we can also, factoring in then the mass of the gas molecules. And what we will see here essentially is that there is a direct relationship between temperature and speed. So at any given temperature, we're going to have a distribution of speeds. So for different gas molecules, but we're going to have an average speed based off of the average kinetic energy. What we'll see is that at low temperature, we'll have one kind of distribution, but as we increase the temperature, that will increase the average speed, and so we'll shift that whole distribution of speeds to a higher value. Now, there are several different measures of molecular speed. There's the most probable speed, which is the one at the top of the distribution here, which is just, that's the number, I guess the speed that's exhibited by the largest number of molecules. And then there's the average. Since this distribution is not perfectly symmetrical, the average is not the most probable speed. And so this would just be the average of all the molecules. And then there's the root mean square speed. This is the speed of a molecule whose kinetic energy is equal to the average kinetic energy of the whole system. All of that can be confusing. There's really one primary equation that I would like to pull out that we will use, and that is simply the equation for the root mean square speed of molecules. So this equation relates the speed of a molecule whose kinetic energy is equal to the average kinetic energy of the system to the temperature of the system and the molar mass of the gas, as shown here. Now, why is the symbol U given for speed instead of V? I cannot tell you why that is the case, but it is. So U is used for speed here, where RMS is given as the root mean square, indicates this is the root mean square speed. You can look up in your textbook for the equations for the average or most probable speeds. But the main point out of all of this is that the speed of gas molecules, or the average speed, is directly proportional to the temperature and inversely proportional to the molar mass. I'm going to sort of show this in this next picture here. So this is a case where the temperature is constant, and we just are looking at multiple different gas samples. And what we'll notice is that the speed, the average speed, is the greatest for hydrogen and the least for oxygen. And that tracks with the molar mass. So the molar mass is the lowest for hydrogen and the greatest for oxygen. And so since those two are inversely proportional, hydrogen has the greatest speed with the lowest molar mass. Oxygen has the least average speed with the highest molar mass. All right, let's put this together. How do we actually use this equation? Remember, the overall point here is we're just trying to be able to relate temperature and molar mass to determine an average speed, in this case, the root mean square speed of the molecules in the gas sample. So what is the root mean square speed of molecules in a sample of CO2 at 37 degrees Celsius? So all we've been given is the formula and the temperature. That's all we need, because we've got temperature and molar mass in our equation. So first thing to point out is that we need to choose the correct gas constant. What gas constant do I use here? I don't have pressure in this equation anywhere. So I don't want to use a gas constant that involves pressure units, because I won't have anything to cancel it with. So I don't want to use the normal liter atmospheres per mole Kelvin. I don't want to use the liter torr per mole Kelvin or the meters cubed pascals per mole Kelvin. That leaves me with joules per mole Kelvin or calories per mole Kelvin. I'm going to use the joules per mole Kelvin. That's the one I want to use, and I'll explain why in a moment. The reason that I want to use the joules per mole Kelvin is that the final units that I want to come out with are meters per second. I need to have some unit that will allow me to relate things in terms of it that has meters and seconds in it, and joules does. So 1 joule is actually 1 kilogram meter squared per second squared. And so as a result, this unit of joules per mole Kelvin, 1 joule per mole Kelvin would be 1 kilogram meter squared per second squared times mole Kelvin. So this will be the unit that I substitute in with the 8.314. Let's see how this works. So my molar mass, I calculate that just by summing up the atomic weights. That's 44.01 grams per mole. But additionally, if I look at my units for the gas constant, I have kilograms, not grams. So I have to convert this to kilograms per mole so that my units will match. So I do that, I simply divide by 1,000 to get me to kilograms per mole. And then now I substitute these values in. So the root mean square speed is equal to the square root of 3 times the gas constant, 8.314 kilograms meter squared per second squared mole Kelvin, times the temperature, which has to be in Kelvin, so 37 plus 273 Kelvin, divided by the molar mass in kilograms per mole, so 0.04401 kilograms per mole. And now I'll notice that kilograms will cancel, moles will cancel, Kelvin will cancel, and I'll be left with just meters squared per second squared. That works out well because it's a square root. So when I square root the number inside, I also square root the units. And so meter squared, the square root of meter squared per second squared is meters per second. And I now come out with logical units for speed of 419 meters per second. So if you take anything away from this lecture, pay a special attention to the fact that the root mean square speed, or the speed of average speed of molecules, is directly proportional to the temperature, inversely proportional to the molar mass, and it's directly proportional to the square root of temperature, inversely proportional to the square root of the molar mass, and that we must use the 8.314 joules per mole Kelvin gas constant when we are calculating speed, and additionally must convert our molar mass to kilograms per mole so that we keep careful track of our units and make sure that they cancel.